Okay, central limit theorem. I'm gonna show you a visual explaining the central limit theorem and the outcomes of the central limit theorem. Let's suppose you have a population that is bell-shaped that has a mean of 125 and a standard deviation of 16. And I want to draw samples of size, let's say, 9 from this population. So let me select one sample and let me show you what's happening, guys. Just watch. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is what the applet is gonna do. It selected 9 values from the population and it computed the mean of those 9 values, which is right here. Okay, rather than doing just, I'm gonna reset it. Rather than doing just one sample, I want to draw thousands of samples. And what this applet is going to do, it's going to calculate, the sample means of each of the samples, and then draw a visual. And we're going to show you what the visual of a representation, just of those sample means, and you're going to see what the sample means are going to look like. So we're going to select 1,000 samples. So what the applet is doing in real time, it's selecting 1,000 samples and it computes the mean of each sample, and then it will put all those values in a graph. You will see what this graph is going to look like. So this is 1,000. Let's do another 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 9,000 samples. So we already got 9. Let's make them 10,000. Okay, that's 10,000 samples. Okay. What you see in green are the sample means of 10,000 samples. So 10,000 values. We ask Static Crunch to visualize, to show us a visual of this data set, and here is the visual. First of all, you notice the original population is normal, and this one is bell-shaped as well, so it is normal. Look at the mean of the original population, which is 125. What's the mean of this sample means? It's also about 125, 0.04. You can disregard this if you round this to the nearest whole number. Now look at the standard deviation. This is a 16. You guys, you should agree with me that the standard deviation here should be less than 16 because it's a narrower curve. The narrower the curve, the smaller the standard deviation. But look at the standard deviation right here. It's 5.2695. Okay, here's what I'd like you to do as you watch this video. I would like you to take the standard deviation 16 and divide it by square root of 9, which is 3. If you divide 16 by 3, guys, you will get 5.33. If you round this one to one decimal place, will be 5.3. And if you divide 16 by square root of 9, round it one decimal place, it will be 5.3. So that would be the standard deviation. Now I'm going to change the sample size. I'm going to reset this one, and I make the sample size, for example, 16, guys. Okay, we're going to draw samples of size 16 now. Let's do thousands of them. Another 1,000. More. Okay, that's enough. 7,000 samples. What do you notice? The original mean is 125, and the mean of the sample means is also 125. Look at the standard deviation. Definitely this is bell-shaped. It looks like, just bell-shaped. And this is also bell-shaped, the original population. But if you take 16 and divide it by square root of 16, what's 16 divided by square root of 16, which is 4? Look at the standard deviation here. It is almost 4, 3.98. Now, guys, we're going to show you a population that is not bell-shaped, like this one is kind of skewed to the right. Okay, let's see. Okay. Let's select the sample size. When the population is not bell-shaped, I'm going to select sample sizes that are bigger than 30. So I'm going to do 36 here. And we're going to do 1,000 samples. Watch. Thousands of samples. So I said 1,000, but we're going to do more than that. Okay, that's good enough. 6,000 samples. Notice, guys. The original mean is 109.97, and this mean is also 109.95, which is almost, the same. Look at the standard, look at the shape of the samples. Sample means it's bell-shaped, although the original population is not bell-shaped. But what about the standard deviation? 25.98, which is almost 26, divided by 6, guys, and if you, which is the square root of 36. And if you do that, you're going to get this number, very close to this number. Let's do another sample. Let's do 49. Let me reset here and do 49 and let's change the shape. Actually, I'm gonna scoot to the left, for example. Watch. Okay, that looks like okay. 1,000 times another 1,000, another 1,000. There's 10,000 samples. Okay, watch, guys. Original mean is 133.4. Look, 133.46, which is very close. The standard deviation, which is 27.67. If you divide this by 7, you should get an answer very, very close, just to this one, which is 3.98. But the interesting part is when you work, just with sample means, you will have a population of sample means that is normally distributed, that is bell-shaped, with a smaller standard deviation than the original population. So this is the central limit theorem. In other words, guys, the central limit theorem says the sampling distribution of the sample means will be bell-shaped. If the original population is bell-shaped, is normal. The mean of the sampling distribution will be the same as the mean of the original population, but the standard deviation, no. The standard deviation of the sample means will be equal to the original standard deviation divided by the square root of the sample size. The only thing that you have to be aware of, if you work with populations that are not bell-shaped, like this one, you have to make sure that your sample size is 30 or more to be considered a large sample size. So this is the central limit theorem. This is what you're going to be learning in section 8.1, and I'm going to take you back now to another video where I can show you some applications to central limit theorem. That concludes the video.